All right, well, welcome back everyone to our second lecture here. So let's go ahead and jump in to circuit components. So here's our goals for today. We'll go ahead and start by briefly reviewing the topics from our previous lesson. And then we're going to dive into greater detail on circuit components. So these are familiar ones like resistors and sources, but also some newer ones like dependent sources and open and short circuits. Also, we'll review the tools that we use to measure circuits in the lab, and we'll solve some more example problems. So feel free to follow along in Chapter 2 of our Circuit Analysis and Design text. Okay, so let's go ahead and start with a review question. And so if you're following along on the handouts, this question is printed toward the end of the handout. And please note that I do like to put at least one of these questions of the day or something similar on exams. So definitely make sure you understand these questions of the day, as I guarantee that you will see at least one of them again on an exam in the future. Okay, so this first question of the day is about chocolate chip pancakes. So I like chocolate chip pancakes, and I'm cooking a big batch with an electric range. And the electric range uses a standard 110 volt wall outlet and a constant current of 10 amps. Notice we've got a voltage and we have a constant current given. We are to assume it takes 2 hours to cook that giant batch of pancakes. So first part asks to find the total charge in coulombs that passes through the range. Second part asks to find the power absorbed in watts. So if you'd like to try this on your own, please pause the video and give this problem a try. And once you're ready, we will go ahead, play the video, and you can see the solution. So I encourage you to take a moment, pause the video and give this a try, and then see if you got the question right. Okay, so let's go ahead and talk through how we would approach this. So let's start with part A. So notice we are given, we know that we have a current of 10 amps, so current I is 10 amps, and we also know that our voltage V is 110 volts, and we know our time T is 2 hours. And so we want to find charge. And remember, charge is our letter Q. In this case, our charge is constant. So the key to this question is remembering how to find charge given this information. So how is charge related to the given information? So big thing you want to remember is that from last class, we learned that Q our charge Q is the time integral of current. And notice we know that this is just 10 amps. And what was our time? Our time was 2 hours. But be careful, because remember, amps are in coulombs per second. So we need to change 2 hours to 7,200 seconds. Because remember, 1 hour is 3,600 seconds. So we need to convert. So be very careful about those unit errors. So notice, all we need to do here is integrate, and we can find our desired result. So let's integrate. So in this case, Q will be the integral from 0 7,200 seconds of 10 dt. And so if we take our integral, that will be 10t from time t equals 0 to time equals 7,200. And so finally, we determine that our charge Q will be equal to 10 coulombs per second times 7,200 seconds, which gives us 72,000 coulombs. All right. Hopefully you got the same thing as I did. Again, be careful of the units here. And remember to convert hours to seconds. All right. So now let's continue with part B. We want to find the power absorbed by the range. Well, how do we do that? Well, let's remind ourselves, how would we find power knowing these things? We know I, V, and T, and we also know that power is current times voltage. So all we need to do is substitute. So in this case, our power P becomes 10 amps times 110 volts. We multiply that through, and we get 1100 watts. So there you have it. Not too bad, right? Hopefully you found this example to be fairly straightforward. Just make sure you be careful of those units and keep these equations handy. As we mentioned last time, knowing these relationships is very, very important for our class. All right, there's a cleaner solution if you'd like to look. And now let's go ahead and jump in to a little more review. How about one more review question here? You'll remember we talked about the passive convention. The passive convention helped us determine whether a circuit is receiving or supplying power. So see if you remember. To satisfy the passive convention, which terminal does current need to enter? Take a moment and think about it. Did you remember correctly that it was positive? Make sure you remember the passive convention. All right, so once again, just a refresher, remember that cheesy water wheel analogy. It's kind of silly, but it can be really helpful. So remember, one way to visualize current flowing in this element is to think of it as a water wheel. If current enters the positive terminal, that means that we're starting at a higher voltage or a higher potential. That means our current is flowing downhill. To the lower potential. And so you might remember, if our current is flowing downhill from higher to lower potential, that means that the element will absorb. The element will absorb power. So by the passive convention, if we have current entering the positive terminal of our circuit element, then that means this element, if power is positive, this element is absorbing power. And of course, as we discussed last time, if the opposite is true, if current enters a negative side, that means our water wheel has to do work on the current in order to push the current uphill. So if the opposite is true, then our power will be negative and the element will be supplying power. So make sure you remember that passive convention. And if you have any other questions on this, feel free to reach out. Let's try another review question. So here we have a circuit element, and we are given that this voltage V is 5 volts, and we are given that the current here is 2 amps. First question, do we meet the passive convention? Second part of the question, are we receiving or supplying power? Take a moment and think about it. Go ahead and pause the video. So, what did you come up with? Notice that current enters the positive terminal. That means the passive convention is met. And notice that the power is just 2 amps times 5 volts. It's 10 watts. Power is positive. That means, in this case, power is absorbed. Since the passive convention is met. And so the correct answer here would be, in this case, passive convention met, and we are receiving or absorbing power. So correct answer was choice C. All right, let's try one more review question. So now we have our voltage V is 5 volts, current I is 3 amps. Once again, we're asked, does this circuit element meet the passive convention? And are we receiving or supplying power? Take a moment and think about it. Go ahead, pause the video, and then let's discuss. All right, this time, did you find the correct answer? You should see that the passive convention is not met. That's because current is entering the negative terminal. So passive convention is not met, and notice that in this case our power is equal to IV, which is in this case 3 amps times 5 volts is 15 watts, but notice we have to pump that 15 watts uphill. So if we draw our water wheel, you can see this element A is going to have to supply power because this 15 watts must push element A up. So in this case, our passive convention is not met, and therefore, since our power is positive, the element must be supplying power. Hopefully now this is starting to make a little more sense. And if you still have questions, feel free to reach out if you have any last questions or something's not clear. And very often I will put a question similar to this on quizzes and exams, so make sure you remember this. Okay, so let's go ahead and move on then. So today we're going to take a deeper dive into different types of electrical components. So there's two general types of electric components. There are active components and passive ones. So a passive element is something that absorbs energy. Think of a resistor. The resistor itself is not producing any power. It's simply sitting there and absorbing whatever current or energy passes through. In contrast, an active element can supply energy. So these are things like voltage and current sources. So make sure you know these two terms and the difference between them. And so in the next few slides, we're going to go through some examples of different common circuit elements. So feel free to follow along in the handout as we go through these. So first one, resistors. So a resistor is a circuit element that has some resistance R. And you may recall, resistance is the physical property that impedes current flow. It resists current. Symbol for resistance is R. Units of resistance are ohms. Remember, 1 ohm is 1 volt per ampere. And the symbol in the circuit diagram is just that zigzag line. So there's a few important equations for resistors that we definitely want to know. First one is Ohm's law. So you may recall the classic V equals IR. Some books like to write R as a constant and I as lowercase because current and voltage may be changing. Important thing is to watch your units. Make sure your voltage is always in volts, current is always in amperes, and resistance is always in ohms. If you have millivolts, kiloohms, milliamps, remember to convert units. You don't want to accidentally have your answer be off by 1,000 if you forgot to convert. And for this class, we generally assume resistors follow passive convention and have linear behavior. Another favorite equation for resistors is that equation that power through that resistor is equal to current squared times resistance, or voltage squared divided by resistance. And these just come from substituting Ohm's law into P equals IV. And once again, be careful of the units on those. Make sure you convert if you need. Last bit of information here is more for your information. I'm not going to ask you about this on any exams, but if you want to think about where resistance physically comes from, it comes from the property called resistivity, and typically it's determined based on the actual area and volume of the component. Again, I don't expect you to remember resistivity and this stuff for exams. One other thing to note about Ohm's law is there's also this thing called conductance. So conductance is given the symbol G, where G is equal to 1 over R. Conductance is the inverse of resistance. So conductance is how easily we allow current to flow. So sometimes you may see Ohm's law written in terms of conductance, and the unit of conductance is the Siemen. So in this class, we deal primarily with resistance, but just an FYI, if you ever see conductance, that's what it is. It's just the inverse of resistance. All right, let's move on to our next component. So again, now we're moving to some active elements, our voltage and current sources. So in general, a source is a voltage or current generator capable of supplying energy to a circuit. And ideal sources use a circle as a symbol. So here we have an ideal voltage source. And down below we have an ideal current source. So let's talk a bit about these sources. There's a few terms here that do come up. First is this idea of an independent source. An independent source is not dependent on any other circuit variables. It will give the same value no matter what is going on around it. So if it's a 2-volt source, it's always going to give you 2 volts, even if you have a million resistors connected to it. So an independent source, it doesn't care what's happening, it's always going to give you the same value. As you might expect, this may or may not be physically possible all the time, but it's an assumption that can help us simplify things. Next, we have an ideal source. An ideal source means the behavior is independent of how much current or voltage is passing through. So what that means is that we can deliver infinitely high voltage or current. We never max out or saturate. You may have seen this in real life if you try to connect something to a very small battery. Eventually, a very small battery will not be able to deliver enough voltage and current to support a giant load. Eventually, the amount of energy it can provide hits a maximum. But in an ideal source, it could deliver infinitely high voltage or current based on the situation. One other thing to note about sources, typically we assume positive current flows out from the positive terminal of the voltage source. And again, that's because current is flow of positive charge, so current wants to flow from positive back to negative. And then, of course, with a current source, the direction of the arrow specifies what way the current will flow. All right, so let's try another example. And if you'd like to follow along, these examples are in your handout. So here, suppose we accidentally left our headlights on. And so we assume our car battery is a 12-volt ideal voltage source, and our headlights are a 6-ohm resistor. And we also are told to assume our battery can store 1 million, or 10 to the 6 joules, when fully charged. First part, what current is provided by the battery? Take a moment, see if you can solve that. Do you remember what equation we should use? Were you thinking to use Ohm's law? Remember, voltage is current times resistance. So in this case, 12 volts is current times 6 ohms. So all we need to do, solve for I. We determine that our current I is 2 amps. Let's move on to the next part. Next part asks, how much power is used by the headlights? Think about how you would solve that. Pause the video if you need. So recall, we know that voltage is 12 volts, current is 2 amps, and our resistance is 6 ohms. So what we need to do here is plug into a power equation. So in this case, hopefully you determined that just multiply together, we should determine our power is 24 watts or 24 joules per second. All right, let's move on to the last part. This part asks, how many hours will it take to drain all 1 million joules from the car battery? Let's assume our battery is initially full. So pause the video for a moment and see if you can solve this one. So there's one important piece of information that you need to remember to solve this part. Remember, 1 watt is equal to 1 joule per second. And we just found, we know from part B that the battery uses 24 joules per second. We are also given battery holds 10 to the 6 joules. So a couple ways to solve this. We can simply integrate using the integral energy is the integral of power. Or since everything's constant, we can simply divide. So in this case, we can do some division and say, okay, well, if we have initially 1 million joules divided by 24 joules per second, that tells us that it will take 41,667 seconds to drain 1 million joules. Are we done yet? Wait a minute. The question was asking for hours, right? So let's convert to hours. We have 41,667 seconds times 1 hour is 3,600 seconds. So we divide 41,000 by 3,600. We get 11.57 hours. So about 11 and a half hours to drain that car battery to zero. All right. And there's the solution if you'd like a little cleaner version. Okay, so let's go ahead and move on. And if any of this have any questions about any of these things, remember you're welcome to reach out by help hours or Discord if you need. Let's continue our discussion of components. Next, we have open and short circuits. Believe it or not, these are actually very, very important, and they come up a lot. So an open circuit is an ideal current source having zero current. So it's literally like a broken wire. If a wire is broken, no current can flow through there. You can also think of it like a dead end. One thing to be careful of, though, just because the current I of t is zero doesn't guarantee that the V of t across the open zero. It depends on the rest of the circuit. So be careful there. Just because current is zero across those 2 points, that does not necessarily guarantee that voltage will be zero. You can also think of an open circuit like a resistor with infinite resistance. Next is short circuits. You may have heard of short circuits if you've done any soldering work with electronics. A short circuit can happen if 2 points unexpectedly become connected. And so a short circuit is modeled by an ideal voltage source having zero voltage. Basically, a short circuit is like a plain resistanceless wire. It's just a wire. It's just 2 points that are connected, and there is no voltage difference between there. When I see the word short, I think of shortcut. We can travel across that circuit without losing any voltage. So notice voltage across a short circuit is always 0. So once again, a word of caution. Just because our voltage is 0, that doesn't guarantee that the short circuit's current Just because voltage is 0, that does not guarantee that the short circuit's current will be 0. Sometimes a short circuit will have a non-zero current flowing through, so be careful. It depends on the rest of the circuit. And physically, it's very similar to having a resistor with 0 resistance. Let's try an example. Best way to learn this stuff is by example. So here's a question for you. What is I2? Pause the video and take a moment to think about it. Question to you. What is this? This is an open circuit. How much current flows through an open circuit? It has to be 0. So in this case, that means since there's no current entering, there can't be any current leaving. There's no current through this whole part of the circuit, so I2 must be 0. Let's try another example. Go ahead and pause the video if you'd like, and give this one a try. Here we're being asked to find the voltage drop across R1. Question to you, what is this? Notice, this whole thing is short circuit. This is a short circuit. Short circuits have 0 volts across them. Well, what does that mean? That means there is 0 volts from point A to point B. That also means if there's 0 volts, this entire area is connected. Right? Because if there's 0 volts, it's as if this whole thing was connected by a resistanceless wire. Well, wait a minute. If there's 0 volts from A to B, there's also going to be 0 volts across the 2 ohm resistor, 0 volts across the 3 ohm resistor, and 0 volts across the 6 ohm resistor, because notice there's 0 volts across the resistor, and our resistance is non-zero. There is no current. No current will flow through the 6 ohm, 3 ohm, or 2 ohm resistors. In fact, we could actually redraw this circuit as something like this. Because remember, this whole thing is connected. So notice the only resistor that experiences current is R1. All the other resistors have 0 volt voltage drop. So that means that R1 has a 12 volt voltage drop, because all of the voltage source's voltage is going to be dissipated by R1, and the rest of the circuit is connected by that short. This is very important. If any of this stuff is still not making sense, please do make sure you reach out if you have any questions. Let's go ahead and continue on. The next circuit element we're going to cover is dependent sources. These might be new for you. It's not typically covered in physics class. A dependent source models the situation when voltage of current. Dependent sources model the situation in which voltage or current is proportional to voltage or current of a second element. And really, in real life, this is a model for a transistor and an amplifier. There's really no physical equivalent of a dependent source. The best analogy I can think of is a water faucet. So if you think of a water faucet, you have some water flowing out, but the amount of flow depends on the handle. So basically, it depends. The flow coming out of our faucet depends on something else. In this case, it's how much the handle is turned. So once again, dependent sources electrically are basically the same thing as this water faucet. It's basically a model for a transistor or an amplifier, and we'll cover those in more detail a bit later. So for now, what you need to know about dependent sources is first that we use a diamond as the symbol. So notice dependent current source is a diamond with an arrow, and diamond with plus minus is a dependent voltage source. couple more things to know about dependent sources. There's always going to be two parts to a dependent source. First part is the controlling part. So that is the thing that determines the behavior of the source. That's like the handle on the water faucet. It controls the flow. Meanwhile, the controlled part is the thing being controlled. That is your actual voltage or current source. So in our class, we focus on four main types of dependent sources. We can have current-controlled voltage sources, voltage-controlled voltage sources, voltage-controlled current source, and current-controlled current source. I wouldn't worry too much about memorizing all these. We'll cover a strategy on how to solve any dependent source in just a moment. So here's the approach I recommend for analyzing dependent sources. And unofficially, before you start analyzing anything, you should be happy. The reason why is because dependent sources, they give you free information. Notice here, for example, the dependent current source. The amount of current exiting this source is equal to 0.2 times V, where V is over here. So notice we're given a free equation. If we know our value V, then we automatically know how much current is coming out of that source. Similarly here, the dependent voltage source, our voltage V is equal to 5I, and so if we know our value I, we can determine our value V. So these equations, an equation will always be given showing what the source depends on. So notice, typically it will be a constant times some other value. For example, this 5 is a constant and the value I is a current. We also call the number 5 here, that constant, we call it the gain. So in this case, gain is whatever value we're multiplying the dependent thing by. So once you know what the source depends on, then you can just figure out how much the source is outputting. They're really not so bad. One of the best ways to get comfortable with these dependent sources is by doing some examples. So let's give it a try. Suppose we have this voltage-controlled voltage source. So question's asking, how much power is absorbed by this source? Well, first we need to be happy because we got free information. We know that we have a dependent source. Second step is we want to see, what does the source depend on? Well, in this case, the voltage V coming out of our source is equal to 2V, where notice this V is the voltage across our 2 ohm resistor. So notice we need to find this value to determine the voltage across our dependent source. In this case, it's a voltage-controlled voltage source. Well, wait a minute. Do we know what V is? What is this little v? Hey, wait a minute. We've got a voltmeter there. We're given that V is 2 volts. That means V dependent is 4 volts. Now we can solve this problem just like normal. Go ahead and take a moment, see if you can solve this problem the rest of the way, and we'll go ahead and discuss. All right, so let's just briefly talk through this. So we determined that our little v across our 2 ohm resistor was equal to 2 volts, as the voltmeter told us. So that means the voltage across our voltage-controlled source voltage here is 2V, or 4 volts. We want to find power across that source, and we know that power is current times voltage. We know that this is 4 volts. Do we know our current? Hey, wait a minute. The ammeter tells us from the ammeter, we know that our current I is 1.5 amps. So notice that current is entering the positive part of our voltage-controlled source. And we can determine, in this case, our power is simply 1.5 amps times 4 volts. That gives us 6 watts. Since current enters the positive terminal, we know, in this case, that our current is absorbed. So that wasn't so bad, right? You should be happy when you see dependent sources because they give you free information. All right. And there's our solution. All right, so let's go ahead and do one more example here. And if you'd like, I'd encourage you to pause this video and try it yourself. Otherwise, I'll briefly explain it. Here we are asked to find the current delivered by our current source. So let's take a look again at this question, and we can notice immediately that we know IS is given by 4IA. So again, the 4 is the gain, that's the constant that the dependent thing is multiplied by, and IA is the thing controlling the source. Do we know IA? Let's take a look. Well, IA is entering, and we know that we have negative 1.2 amps. So what can we say about IA? From the ammeter, we can say that IA is negative 1.2 amperes. So therefore, we can conclude by substituting, we determine that IS is just 4 times negative 1.2 amps. That gives us our IS is equal to negative 4.8 amperes. Not bad, right? Dependent sources really aren't that scary once you know how to deal with them. All right. So let's go ahead and move on to the second part. So second part here, we're asked how much power is produced by that current source? And then finally, does the current source receive power or supply power to the circuit? Take a moment and give it a try if you'd like, and then we'll discuss. All right, well, we know P is equal to IV. And from our previous question, we know that IS, the current supplied by our source, that's negative 4.8 amperes. So we know I. We need to find V. Do we know V? Well, turns out we do. V is 24 volts from the voltmeter. So we can plug in. And let's draw a little picture here. Notice we have negative 4.8 amps passing through our source. And notice that our voltage here is 24 volts across the terminals. So notice because of the negative sign, we could also instead write that we have positive 4.8 amps entering the negative terminal. So notice this is a good time to whip out our passive convention. So we can determine that our power P is equal to IV, which in this case is equal to our 4.8 amps times 24 volts. We multiply that through, that's 115.2 watts. Notice our 4.8 amps is essentially entering the negative terminal. So passive convention is not satisfied. So the power must be supplied. Another way to visualize this is to look at our water wheel. We've got negative 4.8 amps, a height of 24 volts. So our source must supply power. All right. And there's our solution. Okay, we have just a few more topics for today, so let's go ahead and finish up our last couple topics. First is transducers. And for now, all you really need to know about transducers is that they are devices that convert physical quantities to electrical quantities. And two very common ones are potentiometers and temperature sensors. Potentiometer converts position to resistance. It's like a volume knob. If you have an electric device with a knob that turns. Also, temperature sensors. They convert a temperature to a current. Or sometimes they use a temperature-sensitive resistor in order to do that measurement. So if you think about like your kitchen thermometer or many temperature sensors on the market, they rely on electrical sensors. All right, let's go ahead and talk now about switches. Switches are really important. And in this class, we typically model switches as shown here. We assume a switch acts as a short circuit or plain wire when closed. And then when the circuit is opened, we assume it acts like an open circuit or broken wire. And so remember, of course, that broken wire, we have zero current. And when closed, we have zero voltage across the switch. We also assume that the transition between the two positions happens instantaneously. And so whenever you have a switch problem, you want to take a close look at the text next to the switch. Notice in this first example, we have an arrow pointing downward. So this first switch here was initially open, and it closes at time t equals 0. In the second case, the switch opens at t equals 0, but before then, the switch is initially closed. This first type of switch is called SPST, single pull, single throw. These types of switches open or close a single path. Another type of switch is called SPDT, single pull, double throw. And basically, it can alternate between two paths. So it can either open A to B or A to C, depending on the position. Key thing to remember here is to pay attention to the text next to the switch. And draw pictures as needed. And drawing pictures can really help visualize the circuit when the switch is flipped. So let's take a look at an example. These examples are really similar to problems that appear on homework and even on exams. First question asks, what is the current at t equals 1 second? Go ahead and give this problem a try. Pause the video if you'd like. Okay, so important thing to notice here is to first think about what is the position of the switches. Well, at time t equals 1 second, this one is still open. So there's no current flowing through the left portion. So there's no current through that switch on the left. How about on the right? Oh, well, since this opens at 2 seconds, but we only have 1 second past, this switch is closed. So we can actually redraw this circuit to look something like this. So notice here, no current flows through this portion. It's as if this circuit was simply a 10-volt source and a 5 kilo ohm resistor. That 15-volt source is completely cut off. Now it's a little easier to find that current, right? Well, we can just use Ohm's law. And if we use Ohm's law, notice we can determine that voltage is current times resistance. And our resistance, again, watch units, our resistance is 5,000 ohms. So if you solve for current, you'll get a current of 2 milliamps. Notice that drawing a picture really helps. Don't be afraid to draw pictures. Let's try another example. Again, there's the solution. Let's try one more. So in the second one, we're asked current at time 4 seconds. So go ahead, pause the video. See if you can get the right answer. All right, well, at time t equals 4 seconds, notice what happens. This switch is now closed, but then our switch on the right is open. So notice what happens here, kind of the opposite as before. We have our 15-volt source, have our 5 kilo ohm resistor, and notice this time our 10-volt source is completely isolated. No current flows through that right branch. So it's as if our circuit looked like this. All that's left is to solve. we determine that our current I, in this case, will be 3 milliamps. So once again, please don't be afraid to draw pictures. It really does help, especially with questions like this. All right. So finally, we have one last topic for today, and that's to finish up with voltmeters and ammeters. And we'll also briefly touch on a few cool applications. So just to review, voltmeters and ammeters are used to measure voltage and current. So as we saw in our example, voltmeters measure voltage across an element. And remember, you put your voltmeter in parallel to the element when you're measuring it. As you can see in this picture, voltmeters act like open circuits, so we assume that no current will flow through the voltmeter. Voltmeter is just measuring a voltage across that open circuit. So make sure you remember, voltmeters need to go in parallel to the element that we're measuring. And if you have a circuits problem with the voltmeter in it, we can safely assume that there is no current flowing through the voltmeter portion. Next is ammeters. So remember, ammeters measure current, and the ammeter needs to go in series to the element you want to measure. This is because ammeters behave like short circuits or plain wires. Ammeters have zero voltage across them. So remember, the ammeter behaves like a plain wire. So the ammeter is not going to add any voltage to our circuit. It's purely going to measure whatever current happens to be passing through. All right, final few points to remember about voltmeters and ammeters. First, remember the color code. The black probe on the ammeter is the negative, and the red or the colored probe is positive. Notice in some books the red probe might be blue or some other color. And when you're measuring stuff in the lab, remember you want to generally put the red or the positive probe on the positive terminal of the element. So, like shown here, notice the red probe goes on the positive part. Or in the case of the ammeter, you want to have the current enter the red probe. And finally, of course, the black or the negative probe should be put on the negative terminal of the element. And you would probably see fairly quickly that if you accidentally swap the probes, then you'll get an opposite sign of measurement. So you'll get either a negative current or a negative voltage. And you can just swap the probes to get the reverse sign. Finally, let's end with a couple cool applications. Why do we bother learning about this stuff? Well, first, as we hinted before, a lot of these basic principles are used in resistive sensors. So many sensors in the real world rely on electrical properties like resistance. So we talked about thermistors, which are temperature-dependent resistors, but there's also things that are sensitive to pressure or bending, or electrodes that can absorb chemicals like moisture. And so we can use electrical dependent materials in order to actually make sensors. And these are just some examples of how sensors can be used to measure fluid velocity, or in this case, some moisture. For more info about this, take a look at our textbook, Circuit Analysis and Design. There's a lot of good info in there. Finally, one other cool application is superconductors. So it's maybe hard to imagine a material that has zero resistance, but superconductors can actually achieve zero resistance as long as they are cooled to very low temperatures. For example, liquid mercury has zero resistance when cooled to 4.2 Kelvin. And these things are actually used quite a bit. So in the high-speed trains and in MRI machines, those are two applications where we do need superconductors in order to do the job. So I'm showing you these applications just to help us keep these things in perspective. We're not learning this stuff just for the sake of learning. These electrical principles are important, and they're used everywhere in real life. So I don't expect you to memorize these two applications for an exam, but keep them in mind. And if one of these looks cool, definitely check out the references for more information. All right, so let's wrap up here for today. So hopefully now you have a better understanding of electrical components and the concepts from our previous class. And definitely make sure that you're comfortable with the different circuit elements we've covered. And make sure you remember how to use your ammeters and voltmeters. Finally, I definitely encourage you to go back through the examples on your own and see if you can reproduce the results. By practicing these examples, you'll get a lot more comfortable with the topics. And as always, feel free to reach out if you have any questions on this material. Thanks everyone, and we'll see you in the next video.